let's get started. So welcome to Reyes, everybody. My name is Orlando Ayala. For those of you that haven't been in one of my classes before, I'm an associate professor at the Engineering Technology Department, specifically in the Mechanical Engineering Technology program. I am a mechanical engineer, graduated from Venezuela, and I have been in the field for many years. I'm giving that introduction because I typically give the introduction of myself and the college and all that at the very beginning of the presentation. But since I did it in my previous class, I'm gonna leave it up to you guys to go back to the recorded video and know a little bit about myself and our college. The only thing I wanted to remind you is that the rules of engagement here. So I like to teach you by interacting with you. So please, for real, stop me at any time. Send me questions through the Q&A chat or Q&A button, using the Q&A button or the chat if you have the chat option. But feel free to start asking questions as soon as you have any doubt. And you better do that, because we're gonna start building upon the knowledge that I'm gonna give you slide by slide. So you might want to start asking questions right away so you don't get confused, because today I'm gonna take you through the way we teach students in college. Okay, I'm gonna tell you more about that in next. So the agenda of today's class is I'll cover or revisit the topic of fluids and their properties. And I'm saying revisit because I discussed that in my previous class. So if you took my class prior to this one, then this is just a revisit of those concepts. Then I'll talk to you about hydrodynamics and specifically conservation of mass. We're gonna have fun with that one. I'll talk about forces due to a moving fluid. My previous class was forces due to a stagnant fluid, so fluid was not moving. But this time we're allowing the fluid to move. Turns out that the motion of the fluid could also produce forces in any surface that the fluid is touching. And remember, the forces at the end are things that are, the forces of a fluid are always occurring on a solid surface. And as engineers, we wanna know the amount of that force so we could design the structure. Of that solid. Then, in talking about forces due to a moving fluid, I'll be talking about the force equation. And you'll realize that equation, you already know it, but we're gonna expand the equation that you already know and apply it to a fluid. Then we're gonna apply that force equation into a vane, a specific example. And with that, I'm gonna go into discuss a little bit about the difference between theoretical and experimental work, which is something that I also did in my previous class, but this one been focusing on just on the part of the forces of a moving fluid. Then I'll talk to you about collecting and processing data and the homework assignment if you like to get involved with. Like I said before, in this whole class, you will be involved in activities that a typical college students are involved in. So I'll be teaching you concepts from scratch for very elementary concepts. And as we go along, I'm gonna start giving you more knowledge that is based on the very beginning knowledge that I'm gonna teach you. So I'm gonna start building up your knowledge. Now, when I say knowledge, not only is the physical interpretation of what's going on in fluid, but it's also providing you with tools, and those tools are equations. So even though equations could be boring at times, and one of those that I think that sometimes equations are boring, equations are fundamentals. Those are tools. So we need those tools. So not only I'm gonna teach you the fundamentals, the physical phenomena of what's going on why things occur and so on, but also the equations that do represent the physical phenomena. So with that, let's get into the first topic. And the first topic is fluids and their properties. This is something, again, that I already talked to you in the previous class, but if you were not here, just let's learn. So let me start by defining what a fluid is. And by that, I'm gonna go through the boring phase of reading. So I'm gonna read the theoretical definition of a fluid, and that is a substance that continually deforms or flows, like the ones you see in the pictures, under an applied shear stress regardless of the magnitude of that applied shear stress. Now, the fancy word here is shear stress, okay? That's the fancy word. And as I explained before, all I need you to think about shear stress, that stress is a form of force. It's not exactly equal to force, but it's purely related to force. Actually, it's related to force and the area at which the force is applied to. So every time you see a stress, I want you to think in your mind that that is a force. That's what I need you to think. It's a force. Now, but that type of force is very particular, because that's the type of force that you feel when you rub your hands one against the other. When you start rubbing your hands, you start feeling the heat, right? Things are getting warmer in between your hands. That's because of a stress you're applying. That stress is called shear stress, because the force you're applying in your hands is parallel to the area of your hand. So that's what we call shear stress. When the force is perpendicular to the area, we call it something else, which I'm going to explain to you in a second. But in fluid mechanics, if the force is parallel to the area, like in your hands, right? I'm applying my right hand side is applying a parallel force into my left hand side hand. That is shear stress. If my hand instead applies a force perpendicular, we call it something else, which I'm going to explain to you in a second. But in any case, every time a fluid feels this type of force, shear force, then the fluid tends to deform continuously with non-stop, which is what makes the fluid to move, which is exactly what we're going to be talking today. Now, we're going to focus on this class on liquids and gases, but more specifically in liquids. So everything we're going to be discussing applies to liquid, although many of the concepts that I'm going to be discussing with you also apply to gases, I'll be solely focused on liquids today, okay? Now, the next concept is pressure. That one, remember that I was telling you the shear stress are the ones that are parallel to the area? Well, if the force is perpendicular to the area, then that's what we call pressure. And the pressure is calculated by that force, like I told you before, divided by the area at which that force is applied to, all right? Now, very quickly, the pressure, that value of pressure is related to how fast the molecules of the fluid, of the liquid in this case, move. The faster they move, the faster they collide, they hit the wall, hitting the wall, the larger the pressure. So the pressure is fully related to the rate of collision, how fast those molecules collide. And as you could imagine, think about this, put your hands and imagine molecules hitting your hand, right? Those molecules hitting your hand, the faster they hit your hand, the larger the pressure you are supposed to feel on your hand, okay? And please write that equation down because we're gonna need it for something later. So I'm gonna give you, go ahead and get a piece of paper and a pen or a pencil and write that equation down. Say P equals to F over A, and P being pressure, F being force, and A being the area at which the force is applied to. So please write it down. Okay, let's move on and keep the piece of paper next to you because I'm gonna start asking you to continuously write equations, because at the end, many times to better understand the physical phenomena of anything, we might want to rely on the equation because the equation tells us how it behaves mathematically. One thing important, like I said before, that force due to the pressure is always perpendicular to the wall, like you see in the picture. It's always perpendicular to the wall. Shear stress is parallel to the wall, whereas pressure is perpendicular to the wall. The other concept I wanted to talk to you is about a property that you might have heard before, which is density. And density is a property that it tells you the value of density gives you a sense of how much matter could fit in a specific volume. How much matter could it fit, or how many molecules? See, the larger the density, that means that I can fit many molecules in a particular volume, okay, of a particular substance. A lower density implies that I can only fit certain amount of molecules. That's all it means. And we calculate the density by taking the ratio of the mass divided by volume. And mass, of course, is related to the amount of molecules. The next equation that I'd like you to learn or remember, because perhaps you know them already, is weight. And weight is equal to mass times gravity. Okay, that's how much weight I have in my body. I just take my mass, multiply by gravity, and that's the fourth force called weight. Now, if you could see here, let me see if I have the pointer. Pen color, laser color, red. If you could see, density has mass in it. So it's like if I solve for mass in this equation, I'll have that mass is equal to density times volume. Once again, by using the definition of density, I get that mass is equal to density times volume. So if I plug that equation in here, then I get that the weight is equal to density times gravity times volume. And please write those equations down. Write those two equations. First, density is equal to mass over volume. And the other one is that the weight is equal to density, gravity, times volume. I'd like you to write those equations because we're gonna need them in the future, in the near future, okay? I'll give you a few seconds. Once again, density is equal to mass over volume, and then weight is equal to density, gravity times volume. So far we have 3 equations, one for density, one for weight, and another for pressure. So far, 3 equations. Let's move on. And those are just definitions. Now that you know the basic definitions we need for today's lecture, let's get into the hydrodynamics and conservation of mass. But for that, I need to introduce another concept that we use heavily in fluid mechanics, and that is mass flow rate. So what the heck is mass flow rate? Well, let's get into that. But before, I'm gonna show you a video. Let me see if I can control the video. Yes, look at this. So what I have there is a wire that can release bubbles of hydrogen in water. So water is moving from left to right. Water is moving from left to right. And I have a wire that you can barely see, okay? I have a wire that you can barely see in the video. And the wire at some point started releasing bubbles of hydrogen. And all you see there is bubbles of hydrogen. Now, why do I do that? Well, I like to do that because the bubbles of hydrogen are so light that they are carried by the flow precisely. So whatever I see, because that's true, because the fluid can carry those bubbles precisely, whatever I see of those bubbles behaving, I can definitely assume that that's the behavior of the fluid. See, fluid is, when you see a fluid, it's difficult to see its motion, all right? It's difficult to see its motion, so we have to come up with experimental techniques to see it. So this is an experimental technique where I release bubbles of hydrogen just to see how the fluid moves. And in this case, it's just a very simple experiment where I see that the fluid definitely goes from left to right. But this is one thing that I want you to think about it. If I want to measure the amount of mass passing through the wire, and let me stop this right here. If I want to measure the mass of water crossing the wire, the amount of mass that just crossed the wire, all I need to do is to get a chronometer, okay? Let it run, and then stop it. So I can let it run, boom, and then I stop. See, when I stop, I can go and measure, right? This length, the length right here. This length represents the amount of water that just passed the wire within 1 second. Let me see if this is 1 second so I can repeat it. So let's say I'm gonna start it. Where does it start? Right here. So look at this. This starts at 2 seconds 2.4 seconds. I'm gonna let it go for half a second. Boom. Oh, I should have stopped it here. Sorry. Half a second is around here. Actually, half a second is right here. Let me start it again. So I'll start from 250, let's say, and then I'll stop at 350. Around 350, right? So I know that within 1 second, this is the amount of water that just passed the wire. And I can measure that because, see, I have the video. I can get a ruler and measure that. And by measuring that zone, that region, I can get a sense of how much mass of water passed the wire. Now, keep that in mind. Let's go into the next slide. So what's mass flow rate? Let me do the same experiment, but let's imagine that experiment inside a pipe. And the reason I'm doing a pipe because it's easier to manipulate, to create equations with a pipe. Why? Because I know a cylinder. I know how the geometry of a cylinder. So I'm gonna go into a pipe, same experiment, but assuming that the wire is at one point in the pipe. So here we have, let me draw something here. So let's say right here is the wire, okay? I just put the wire right here and do the same experiment. I start my chronometer and I stop it. Once I stop it with a delta T, I can come here to measure this shaded area. I can measure this shaded area now, okay? Now, if I measure that shaded area, I can get a sense of the mass, of the amount of mass. And now notice that, but before going to the next slide, mass flow rate is the rate of mass passing through that area. The area where the wire was. The area where the wire was. So all I need to do is to measure that mass, if I have a way to measure that mass, divided by delta T, that will give me mass flow rate, which is this equation. So mass flow rate is nothing but the mass that just passed the area divided by the delta T that I use in my chronometer, the 1 second I did with you in the video, okay? Now, from the 3 equations you wrote down, I'd like you to use the equation for density. Now, the same way we derived an equation for weight containing density, we're gonna do the same thing here. So mass, following the equation for density, the one that you wrote down, mass is equal to density times volume. What volume? The volume of this shaded area. So I'm gonna use that concept. I'm gonna say that mass is equal to density times volume. Here we are. Mass is density times volume. What volume? Once again, the volume of the shaded area. And here's the advantage of using a cylinder. I know how to compute that volume. I know how to compute that volume because that volume is nothing but the area multiplied by the length of the shaded area. So again, the volume is equal to the area that the mass passed multiplied by the delta L. And the delta L is something that I measure because I stopped my chronometer. The same way we did in the video. The same way we did in the video. Now, one thing is that other than measuring this delta L by getting a ruler and going and measure, as I mentioned before, I can also do the following. If somewhat I know that fluid velocity, which every now and then we know it. If I know that fluid velocity, well, I can get this delta L. Because listen, the faster the fluid is moving, the higher that velocity is, the longer that delta V will be for 1 second. So if I, for instance, if I double the velocity and I start my chronometer the same way we did in the previous video, I start my chronometer and stop it within 1 second. If the velocity is double, then that length will be double. If the velocity is triple, then that length will be triple. So I know there is a relationship between velocity and delta L. And I'm pretty sure some of you already know that, because that's what you're learning in your high school. Velocity, the definition of velocity is distance per unit time. Distance per unit time. So I'm going to use that knowledge that you already have from high school. Velocity is distance. What distance? That delta L. Divided by delta T. What delta T? The delta T of your chronometer. So I'm going to use that knowledge and I plug it in here. So I'm going to use the velocity, that concept of velocity, to solve for delta L. Now, look what I'm about to do. What I'm about to do, I'm going to get this delta L, plug it in here in the equation for volume. And then the equation of volume, I'm going to plug it in the mass. Voila, this is what we have. I'll give you 1 second to notice the mathematical manipulation. Nothing crazy, it's just I'm plugging one equation inside the other. And like I told you at the very beginning of this lecture, I told you I'm gonna take you through the process of the way we teach students at college level. That's how we teach. We just give you few very simple equations and we start getting into more involved phenomena where we still use equations that we already know. We start building new knowledge based on the knowledge that we already have. Now, if you see that equation right there, you will notice that this delta T cancel with this delta T. And if I do that, the final equation is that mass flow rate is equal to density times velocity times area. Please note that that velocity must be perpendicular to the area. See, if the velocity is not perpendicular to the area, then the fluid is not passing the area. So I have to have my vector must be oriented towards the area. Otherwise, I won't pass it. It's like when you're leaving a room, you're typically going through a door, right? So look at the door. So the door, oh, well, of course you open the door, but the frame of the door. Now, once you open the door, you have the frame with an empty space that you can cross. That space within the frame is what we call the area. That space within the frame is what we call the area. So the only way for you to leave the room is by crossing that area, which is the same phenomena here. You cross that area. You must cross that area, but to cross that area, you must be moving perpendicular to that area. Because if you move parallel to that area, you're not leaving. You are not leaving, you're staying in the room. The only way to leave the room, to cross the area, is by directing your body perpendicular to the area. So that's why the velocity in this equation must be perpendicular to the area. And my friends, I like you to write that equation down. Please write that equation down. Mass flow rate is equal to density times volume times area. Mass flow rate, which is the amount of mass crossing an area for a particular time, is equal to density times velocity times area. Please write it down. This now becomes your fourth equation. And I need those 4 equations you already have for what's coming next. Now, at the end, I wanted to talk to you about conservation of mass. And what's the law of conservation? What is the law of conservation of mass? It's just that it says that mass cannot be created, neither destroyed, but it only can be transformed. So the mass should always be conserved. The mass should always be conserved, okay? So keep that in mind. That's the conservation of mass. The mass can only be conserved. It's mass coming in, the mass has to go somewhere else because I cannot destroy it. It cannot disappear, neither appear all of a sudden. So let me use that concept for this specific example of water, you pouring water into this tank and then letting water to leave at the bottom of the storage tank from the bottom. See, if the amount of mass I'm pouring into the tank is equal to the amount of mass leaving the tank, then the height of that fluid would not change. Think about that for 1 second. Once again, if this mass getting into the tank is exactly equal to the mass leaving on the other side, this whole thing you see in the drawing should not change, should be stationary. Why? Because of conservation of mass. Once again, mass cannot be destroyed, neither can be destroyed, neither you can create it. It just gets transformed. It moves from one place to another. That's all. That's all. That's conservation of mass. So if these two are equal, then there is no change here. But if the mass flow rate going in is larger than the mass flow rate going out, then the level of the water in that tank will start increasing. Think about that. If I'm pouring more water into the tank than the water that I'm taking out from the bottom, then that tank starts filling itself up. On the other hand, if I'm pulling water out, mass flow rate out, if that m dot out is larger than the in, then the tank will start getting emptied. Think about that. If I open the valve like crazy and I let the fluid to leave and go, and I'm pouring less water, then it starts to get into empty. So it means that it seems like as these two values are different, I am changing the amount of mass in the tank. It seems like as these two, m dot in and m dot out, as they two are different, then the mass in the tank changes. So once again, if m dot in is larger than m dot out, then I'm increasing the mass. On the other hand, if m dot out is larger than m dot in, I'm decreasing the mass. Now, there is a mathematical way of presenting changes, and that's what we call derivatives. But in this case, I'm not going to get into that. All I'm going to say is that m dot in minus m dot out should be equal to the amount of mass that increased or reduced in the storage tank per unit time. That's what it should be. And this is the mathematical formulation of conservation of mass. This is a mathematical formulation of conservation of mass. And these guys applies to anything. It applies to anything. I'm going to give you an example. If you decide to eat 10 burgers like this one, first and foremost, you're nuts. But if you decide to go that route, okay, of eating that many burgers, and then you don't gain any weight. If you don't gain any weight, you are basically the tank that I showed you before. If you don't gain any weight, it's because that delta M is equal to 0. Delta M is equal to 0. So therefore, you must have that the mass that you introduce in your body, it has to go out. It has to go out. Now, you know how our body can get mass out. So all those forms of mass getting out, sweating, I'm going to just say that. The rest, I'm going to leave you to your imagination. But anything that gets out of your body is m dot out. So the only way for you not to gain weight after eating 10 burgers is by having those burgers out of your system, out of your body, by whatever means. By whatever means. I'm going to let your imagination to think what means I'm referring to. So again, this means that whatever you did put into your body must get out. It has to get out. Now, on the other hand, if you do gain weight, that means that you're getting out less than you got in. Therefore, this delta M over delta T is larger than 0. Is larger than 0. It's a positive number. If it is a positive number, then you're gaining weight. And this is what happens typically in Thanksgiving time here in the United States. In the United States, we eat a lot during Thanksgiving time, not letting time to the body to get mass out. Then our delta M over delta T is larger than 0. As a matter of fact, from this point on, every time you have a feast with your family, you can tell them, I'm about to have a delta M over delta T larger than 0, because you're gonna gain some weight. Now, can you get rid of that weight eventually? Yes, you could. Yes, you could. But at that very moment, you'll have a delta M over delta T larger than 0. Now, what if I lose weight? If I lose weight, then that delta M over delta T is negative. It's less than 0. It's less than 0. And you could get that done by doing some exercise or trying to do some exercise. That's the best way to lose weight, by trying to get exercise, because the mass that you have in your body, you're burning that mass. And eventually that mass goes into energy, which is something that I need to clarify. And that's why I always put my note here. See, the human body is so interesting, because in this case, we convert mass into energy. See, that burger will eventually be converted into energy. Of course, it's gonna also be converted into fat, and that goes into your belly and so on and so forth. But part of that humongous amount of burgers that you ate will go as a form of energy. So, and that form of energy is part of the m dot out, because that mass was transformed into something else, okay, into energy. So anyway, this is the conservation of mass law. Like I said, you could apply that to anything beyond fluid mechanics. You could apply that to fluid mechanics. Now, in my class, we typically do not allow accumulation of liquid. In this class, we're not gonna allow accumulation of liquids, neither losing liquid. So this dmdt, or delta M delta T, is equal to 0. Therefore, in my class, and to be honest, in most of the applications in the industry, we assume there is no accumulation. That is not 100% true for anything, but for a lot of the fluid mechanics application, we assume that there is no accumulation. This is something that we call a steady state. So if that's the case, then m dot in is equal to m dot out. I don't need you to write that equation, but I want you to remember that. I want you to remember that the mass flow rate in this class will always be equal. The mass flow rate going in must be equal to the mass flow rate going out. I need you to remember that, please. Now let's get into the core of the concept. Everything that I just taught you, it was an introduction to get you ready for how to compute forces due to a moving fluid. Now, but the first question is, what the heck? Why do I need this? Well, you need it because if you have these kind of situations where you have a river hitting a structure, okay? If you want that structure to be very well designed, I must know those forces. I have to know the amount of those forces, the value of those forces. I need to know how much is that force, because otherwise my civil engineers colleagues are not going to be able to design that properly, this structure. See, if that structure is not big enough, it will be pushed. It will be destroyed. Water could be destructive, very destructive. Have you seen the flooding in the news that have been flooding in Germany, that have been flooding in Japan? Have you seen that? The amount of destruction that water can make? It's crazy. Now, of course, none of the engineers involved in the design of those buildings or the things that you saw destroyed, they were thinking about flooding. We never designed for flooding. Flooding is just something that happens, unfortunately. But because the buildings were not designed for flooding, they got carried away by the water. Now, if I design my building for flooding, I can do that. What happens is that I'll be designing a building for something that could happen once every 50 years. That doesn't make sense economically. It's a disaster, I know, but we, as engineers, we don't design a building for something that it could occur in one time in 50 years. All we do is to design the building and tell people to leave the room, they leave the building if that event occurs. But we don't design because we don't do that kind of design, because if you do, you're making a design, an over design that'll be too expensive. It's too expensive to do. So it is better to play our odds. If it is something that's going to occur once every 50 years, then you just do it. You're just hoping for the best, and that's it. So in any rate, those forces that flooding could cause, the river could cause, I need to know their values, but I need to learn the tools on how to measure that so I can give that information to my civil engineers friends. Same thing for billboards. You see the pole right here? That pole has to be designed in such a way that when a wind blows into this billboard, the pole doesn't flex or doesn't fall down. We can compute that. I'm going to teach you how. I am about to teach you how. And what is interesting is that the equation I'm going to use to compute the forces is an equation that you already know. You already know. Okay? All right. So that's the reason we want to do that. But let me start by giving you an example. Let's say I have a water jet being deflected by a curved vane, like you see in your picture. And you might wonder, well, what case, how does that apply to real life? Well, it does apply to real life because you have played with pinwheels. See that? When you play with pinwheels, all you do, of course, the jet of fluid is not water anymore, it's air. When you blow air in those pinwheels, you're making that to turn. So it's the same thing. The air that you blow, once it gets in contact with the wheel, produces a force that makes the pinwheel to rotate. So it's exactly that application. Now, there is also a reversed application. This is me blowing into the pinwheel, but there is another application. For instance, now I have a fan moving. And because the fan moves, it produces a force that makes the fluid to move. And that is the case of a fan. Or also a pump. The pump that we use in pump station. And also in this one, you see, same thing. But in this case, it's more related to the pinwheels and the more modern one, which is the wind farms, right? The wind turbine. The wind blows along the blades. Those three things are called blades. Okay? The wind blows into those blades, and the interaction between the moving fluid and the blades produces a force, and that force is enough to make the whole turbine to rotate. Well, it's the same thing here, but I just simplified it a lot just to give you an explanation. Now, what's the equation behind this? Because I need an equation. Remember, I need to measure that. That's the whole point. I need to measure that. All right. So all is based on Newton's equation. The same equation you've been talking about for years, for some years or few months, depending on what grade you are in right now. Newton's equation says that the force is equal to mass times acceleration. That exact equation, the same equation. But when you were taught Newton's equation, and that's a law, by the way, that's the Newton's law. We cannot prove that mathematically. Just Newton saw the behavior in nature, and he said, you know what? I can see that force is equal to mass times acceleration. He came up with that the equation mass times acceleration by observation. It wasn't something that he measured. It wasn't something that, sorry, he did measure. It wasn't something that he derived from an equation. He just thought forces gotta be equal to mass times acceleration. Clever mind. Long time ago. 200 years ago, 200 years ago, and now still valid, which although things have changed, is Newton's law is true here on Earth. But if you go to the space, we have what we call the gravity wave and so on and so forth. And that in that case, that equation is no longer true, but it is true when you are sitting in a big, big, big mass like Earth. So near a big, big mass like Earth, that equation is perfect. That equation works perfectly. Okay, but I am going to modify this equation a little bit for something that you know as well. Acceleration is the change of velocity per unit time. Acceleration is the change of velocity per unit time. See, why am I doing this? Why am I about to do this? Because that equation you were taught in high school, or you were taught like a few days ago, few weeks ago, or few months ago. That equation was applied to a little car. That's the typical examples that we use in high school. But here, we don't have a car, we have a fluid. So because we have a fluid, we have to adjust that equation for something related to fluid. And with that, I want you to tell me, what is mass over time? What is mass divided by delta T? Well, that's one of the equations I told you to write down. That's mass flow rate. So when it comes to fluid, where the mass M is not constant, but rather changing, instead of using M, we use M dot like this. And that's the equation we're gonna be using today. And that's the equation we use to design turbines, to design pumps, to design pinwheels, to design fans, and so on. And here's the interesting thing about this equation. Look at that equation. Force is equal to mass flow rate, the one that I told you to write down before, multiplied by the change of velocity. So that means, that right there means that I can increase the velocity by just changing the mass flow rate. Or I can increase or change in general the force by changing the velocity. So once again, I can change the force. Look at the equation. I can change the force by changing the mass flow rate. That's one way of doing things. But I can also increase or reduce the force by also changing the delta velocity, delta V. Now, this, you see that little arrow at the top of the letter? That's what we call vectors. I'm not gonna look into vectors right now. I want you to get into a simpler form. Now, I'm gonna go back to this equation. One thing that I need to mention is that the original equation in reality, Newton's law, is the sum of the forces equal to mass times acceleration. Sum of the force equal to mass acceleration. So I'm gonna use that form. And that means that the equation we're gonna use for fluid mechanics is that the sum of the forces is equal to mass flow rate times change of delta, the velocity. Now, as I was saying before, this whole thing of vectors is boring. All it means is that if I'm in a three-dimensional world, I have three directions. The direction in front of me, okay? The direction sideways of me, and the direction above me. I have always three directions. In a three-dimensional world, once again, I have three directions. The direction in front of me or behind me, the direction sideways me, to my left or to my right, and the direction going up or going down from me. So there are three directions in three dimensions. So because I know that, I can rewrite that equation into three separate equations. The equation from X, the direction X, the direction Y, and the direction Z. And if you like, we can say that the X direction is the direction in front of you, okay? The Y direction is the direction sideways, left and right. And the Z is the direction going up or going down, all right? X, Y, Z. Those are the three directions. That's how we see the world, by the way, in three dimensions, in three directions. Keep in mind that this mass flow rate is this equation, the one that I told you to please write down. And my friends, this is it. This is all I wanted to teach to you. But before we end my hour of class, I want you to spend some time with me using that equation in something in some application. And the first application is the force in an elbow, in a pipe elbow. I'm pretty sure you've seen many of that in your house. You've seen that somewhere else. That the flow, sometimes I need to take the fluid. Most of the time we move fluids through pipes. And if I want to go to my left or my right for any reason, I need to turn the fluid. That turn is what we call the elbow. We use an elbow to deviate the direction of the flow. So that change in direction produces a force right here in the elbow. That change of direction produces a force right here in the elbow. I can measure that force. And how do I measure that force? By using those equations. But the first thing I'm going to notice is that I'm going to use my Cartesian coordinates, like the ones that I told you, my front on my left on my top. Like I said before, in this case, I'm going to call X the horizontal direction and Y my vertical direction. In the Z direction is the one towards the screen. In the Z direction, there is no major changes, so I can eliminate that equation. And now I'm going to focus only on the elbow. I'm going to focus only on the elbow. And I'm going to say that I have my 0.1 and my 0.2. My 0.1 being the inlet of the elbow and my 0.2 being the outlet of my elbow. Now I can apply my equations. But the first thing I'm gonna start identifying is the velocities. Why? Because I have velocities here. So I have velocity 1, velocity 2. Velocity 1 is the velocity at the inlet. Velocity 2 is the velocity at the outlet. Okay. The next thing I'm gonna start, that give me a sense of these terms. And I'm gonna explain to you a little bit in details how this B2, B1 relates to BX2, BX1, BY2, BY1. I'm going to explain that to you in a second. Just wait for a second. And mass flow rate, you know already, that is density times velocity times area. So the right-hand side is clearly drawn in this picture. Probably you don't know how to apply that into the equation. Just give me 1 second. I'm going to get to the point. But the thing is that I want to do is to get to my left-hand side, the forces. So the question is, what are the forces? Well, actually, we still have the force due to pressure. We still have the force due to pressure. Pressure is equal to force divided by area. And I know that at this point at the outlet, I do have a pressure. And if I have a pressure, I have a force. Same thing goes here. I have a pressure here. I must have a force. And I do draw the force. See, the force in this imaginary area is pressure 1 multiplied by area 1. And on the other side, the same thing. The force here is pressure 2 multiplied by area. And that comes from the equation that I told you at the very beginning. There is another force, which is the weight. The weight is also involved in this problem because the water has a weight. The water has a weight. Sometimes it's negligible, sometimes it's not. But I'm going to consider the weight here. And finally, the other force that I have is the interaction between the elbow, the solid elbow and the liquid inside the elbow. See, by the action-reaction law of Newton, as the fluid hits the elbow returns the force with the same magnitude in the same direction and the opposite direction, sorry. So that's there, but I'm going to decouple those two vectors into these two vectors. So I'm going to decouple. So I have a reaction. I have the reaction of the elbow against the fluid. This is Rx and Ry. Okay. Now I have everything identified. So now I can apply my equation. I'm going to start applying my equation to the X direction. So what do I have in the X direction? See, so the question is, how many of those vectors you see in my drawing are pointing in the horizontal direction? And just by eyeball, I can see that P1A1 is horizontal. I can see that RX is horizontal. None of these two are horizontal, so they do not get included in this. This W and this RY are not horizontal either, so I'm gonna include that. The only two that are included are RX, are P1, A1, and B1. So let me start with the right-hand side of this equation. I have my flow rate. What is Bx2? Bx2 is the horizontal component of the velocity 2. So, but velocity 2 is purely vertical. Velocity 2 is purely vertical. There is no horizontal component. Therefore, that Bx2 is equal to 0. That Bx2 is equal to 0. Whereas Bx1 is exactly equal to B1. And this is what we have here. This is 0, and this is B1. This is B1. Now, regarding the forces in this direction, the only two I have is P1A1 and Rx. I plug them in, and this is the equation I have. So I solve for Rx, and remember, Rx is the reaction of the elbow, but since this is all due to action-reaction, this is also equal to the amount of force the fluid is applied against the elbow. Against the elbow. So keep that in mind. Now we have the reaction in the X direction, the reaction of the fluid on the elbow. Once again, see, we just found the equation that will give us the magnitude of the force on the elbow, but only on the horizontal direction. We can do the same thing for the Y direction, for the vertical direction. In the vertical direction, we're going to do the same thing. We're going to identify what terms, what vectors are in the vertical direction. These two are in the vertical direction. RY is in the vertical direction. Y is in the vertical direction. None of these are in the horizontal, in the vertical. None of these horizontal. None of these in the vertical. They are horizontal. And with that, I'm going to start the same thing. So what is BY2? So BY2 is totally B2 because the velocity 2 is totally vertical. The velocity 2 is totally vertical. And By1 is equal to 0 because the velocity at 1 is totally horizontal. There is no vertical component. So that's why I'm going to write the equation this way. And what are the forces in the vertical directions? I have P2A2, but negative, is pointing down. I have Ry, which is positive, and I have W, which is negative, and that's what I have in this equation. Solving for Ry, this is what I get finally. I get that the reaction force, the force that the fluid applies against the elbow in the vertical direction is equal to that expression right there. So guys, yes, you might be overwhelmed here with the many equation, but that is exactly what you're going to be doing here. So this is what happens. During a class, it could get overwhelming, but as you start getting line by line, a good understanding of that, you're going to get familiarized with everything. So don't feel overwhelmed. Don't feel overwhelmed. I know it's a lot. But I told you I'm going to take you through a process of any engineer student. To summarize, we have that the Rx is equal to that. And by the way, that's a good point. I can get this velocity as a function of my flow rate like this, using the equation I told you before. And I can transform that equation, get rid of velocity, and get this equation for the force in the X direction. Okay? And the same thing I can do for the Y direction. So these are right there, are the equations for the force in an elbow, the force in an elbow. Note that the force will increase with flow rate and will also increase with pressure. It will increase with flow rate. It would also increase with pressure. It would also increase with pressure. Now, let me go into another application, but this application is a little bit simpler. It's a little bit simpler. And the reason I'm going into this application is because I'm going to give you the opportunity to go into a virtual lab. I want you to go through a virtual lab to see what you could get experimentally the same equations we get in the theoretically. So I'm gonna apply this to a vane. So let's assume we have this anemometer, and I'm pretty sure you've seen that in many airports. In all the airports, we have an anemometer of this kind, which is a kind of a hemispherical shape, okay? So fluid, when the wind blows, it blows into the shape, right? Once it hits the cone or the hemispherical shape, the fluid just turns sideways. But I'm just for a second, I'm gonna turn it upside down. I'm gonna turn it this way. I'm gonna apply the same equation we know for force, the one that we derived before, this equation. See, notice that in this case, we will always be, we are only concerned in one equation, which is for the force in the vertical direction. We don't care about the horizontal because in the horizontal, nothing happens, nothing is moving. All the motion is vertical. So what am I going to do? I'm going to identify all the forces. I'm also identify what is By2 and By1. So let's start with By2. Well, By2 is nothing but this velocity 2. Okay. Now this velocity 2 is pointing in the downward direction, therefore it's negative. And in this case, By1 is nothing but B1. The other thing to identify is the amount of forces. So before we saw that there is always, every time there is a contact between the fluid and a solid, there is a reaction. So reaction force is there. Now, in this case, we're gonna definitely consider that reaction. But the other forces that we considered before was the weight and the pressure. But in this case, the pressure is the same. Why? Because this is open to the atmosphere. And the pressure in the atmosphere is constant, so there is no pressure change. Therefore, I don't need to consider the pressure. And as far as the weight, I could consider the weight if I like to, but typically the weight of the air is negligible compared to this reaction force. The many amount of words that I just said is just to tell you that we will consider only the reaction. We will consider only the reaction. Okay, so the reaction force is negative because it points downward, right? Is the hemisphere against the fluids pointing downward. Is equal to mass flow rate times minus velocity 2 minus velocity 1. But remember, we can use the equation for mass flow rate and plug it in here for velocity. So I can substitute the velocity, and this is the equation I get. Notice that if I plug this in V2, I plug this in V1, I get that the reaction, the force that hemisphere feels is equal to mass flow rate squared divided by density multiplied by the inverse of the areas. I can do the same thing for a simpler vane. Instead of a hemispherical vane, it's just a flat plate. If I do the same thing, go the same one, see, this will be B1, this will be B2, but see, B2 does not have any component in the vertical direction, therefore it's 0. And then this is equal to B1. Once again, as I said before, I only have the reaction in the y direction, so this is my equation, but using the velocity for velocity, this is the equation I get for R1. Summarizing, if I have a vane that is horizontal, a flat plate, or if I have a vane that is hemispherical, these are the two equations. As you could see, the equations are very similar. The only difference is that in the case of the hemisphere, the term that has the areas, it could be a larger term than this because I'm adding two numbers. That means that theoretically speaking, if I go into the lab and I run the case for a hemisphere and the case for a flat plate, the forces in a hemisphere should be larger than the plate. Should be larger than the plate. And that's what I want you to do in the experiment. I need you to do two things in the virtual lab that I'm about to give you access to. you're gonna run the virtual lab. You're gonna start collecting information to compute mass flow rate and to compute the forces. I want you to start collecting number for the force, which is in this case, we call it the reaction force. And you're gonna start collecting information for the mass flow rate as well. That's what I need you to do in the lab. And I need you to plot that in a graph using Excel. I'm gonna provide to you this Excel file, okay? You're gonna plot that. And I need you to look at two things. Please see first, how the curve for a hemispherical case and the flat plate compare to each other. On paper, looking at the theory, the forces in a hemispherical vane are larger than the forces for a fixed mass flow rate are larger than a flat plate. On paper, let's see what happens. The other thing I need you to look at is how the force depends on mass flow rate. I want you to see that the mass flow rate is to the power of 2. It's a parabolic equation. So what I want you to see when you finish collecting the data, I want you to notice the shape of those curves. I want you to see, is that a straight line? Like in this figure. Is this a parabola? Or is this a polynomial that follows a polynomial of the third order? That's what I want you to see. Theoretically speaking, whatever you see in your experimental work should be like this. Why? Because this curve is for something to the power of 2. Our equations have something, in this case, that something is mass flow rate, to the power of 2. So on paper, we should see something like that. I want you to see whether the data you collect give you exactly that. See, what is the difference between theoretical and experimental work? The theory is pure mathematics, the one that we just did, that could at some point become kind of boring. Experimental work is in a laboratory. Now, with the theory, we can predict magnitudes based on a model. So those equations that we just derived are models that can help us to predict the force. In the lab, we measure those, which is what you're gonna do in the virtual lab. And here we determine analytically the parameters that the force depends on. So we saw how that the force depends on mass flow rate, it depends on the areas and so on. In the lab, we're gonna just measure that to see how they depend on each other. So in the lab, we confirm the theories or equations that we use to design things, because at the end of the day, those equations that I provide to you are very important equations to design things. Remember the example of the floating. We need to measure those forces so we can design our structures. So what are we gonna do? You're gonna collect data, okay? So you're gonna, in an experiment like this, you're gonna see in the video that you have a vane of this kind of hemispherical type, in this kind. You have a water jet hitting the vane and so on and so forth. You're gonna be able to measure the force. You're gonna be able to measure the mass flow rate, okay? And you're gonna plot that, okay? That's what I need you to do. You're gonna start collecting and compute those parameters to see how those parameters affect the force on the vane. In this work, your primary goal is to collect the data and put it into an Excel file that I provide. When you log into the link I'm gonna give to you, you're gonna be able to download that. And then finally, I mean, in this spreadsheet, you don't need to do more things, but theoretically, you could add columns in the spreadsheet if you want to, but for this experiment, you don't need to. And finally, the results can be presented in both in numerical and graphical formats, which you will see in the Excel file. Now, here's your homework. You're gonna go through the video, you're gonna collect the data from those videos, and you're gonna plug those values in Excel spreadsheet that looks like this, okay? Now, as of now, as you get this file, you're gonna see a div 0 in there. Don't worry about that. As you start typing the numbers, that div /0 will go away. Don't worry about it. So you start collecting the data and plug it into the empty spaces in the columns. First for the flat plate and second for the hemispherical plate. All right, now, what happened? All right. What the, this is acting up. Let me share again. I don't know why this is acting up, but it's acting up. Let me go back to where I was. Share screen. Here we go. All right, cool. Sorry, like I said, you're gonna start filling the data up as you start getting it through the video. All right. Now, the calculations in this case are already automatic in the spreadsheet, so you don't need to do that. However, let me present to you what the spreadsheet is doing for you. It computes the reaction force based on the recorded distance, this distance right here. So how far the weight is from the hemispherical plate, the hemispherical vane. So you compute the reaction force this way, and you compute the mass by taking the time to collect 15 liters of water. And the weight of 15 liters per water is given in the video. I mean, I'm giving you the equations right here, but in reality, you don't need them. In reality, you don't need them. The Excel spreadsheet will calculate everything for you and will give you two curves. What I want you to do is to look at these two curves. Do the two curves behave like a parabola? And the other thing is, do the hemispherical case got larger reaction forces than the flat plate? It should, because the theory tells us that the hemispherical should give you larger forces than this. That's all I need you to do. So your goal will be to compare the behavior of those curves you obtained from the experimental measurements and compare them to the theoretical expression. I need you to answer the following questions. Are they the same? Are they similar? And what can you comment? And that's pretty much the homework assignment. Now, you are supposed to go to, let me see if it works today. You're supposed to go to this link, which I'm gonna put the link, where is it? I am going to put the link on the chat. Oh, it's not good. Let's see. And it's not working either. Why is this happening to me? I tested again. I thought it was fixed. Let me give it to you through the, oh. Oh, this is not working. I see. Okay, I know what happened. Is something is not working on my computer. That's why things were acting up. Okay, here's one link to try. And this is another link to try. And guys, try again, because it should work at some point. Let me see if I can get it to work right now. Let me see. Oh, yeah. Sometimes I don't understand technology. Sometimes it works beautifully. Some other times it's just giving you headaches. Oh, I'm using the wrong keyword. Okay, let me show you what it's supposed to look like. If you keep having issues, you got to let me know. Let me share the screen. Right here. Boom. Once you log in, this is how it's supposed to look like. You go to Fluid Lab. Oh, I haven't. Sorry, I haven't enabled this. All right. So once you log in, this is what you're supposed to see. You're gonna click and force you to move in fluids. This right here, the theoretical background is nothing but my presentation, and then you're gonna go through these videos. But the ones that are more important are the ones at the bottom, which is the one that says lab activity. So you're gonna go to the video, and this is a very interactive video. You're gonna just click and start making some clicks to move, follow the instructions at the bottom, and you're gonna move through the video to start collecting the data. Notice that here at the very bottom, you have the click here to download the file. So hopefully this is gonna work for, these links are gonna work for you. And let's see what happens. I'm all ears. I'm all ears to anything that you find out during your virtual lab. At this point, I'm open to any question. And if you don't have any questions, you could also contact me. You know what? Talking about contacting me, let me put my email so you can reach out to me at any time, whenever you want. That's my email in the chat room. Okay. Send me emails if you have any questions, if you'd like to discuss more about this, or if you want to discuss any other thing related to college life. All right. And with that, if there is no questions, I'm going to end my presentation. Do we have any question from the audience? Thanks to you. Thanks to you. So anyway, thank you so much, guys. So I will see you when I see you. Reach out to me whenever you like. I'll be more than happy to talk to you. And with that, I'm going to end the broadcast of the presentation. Talk to you later. It has been a pleasure to have you in Reyes. Hopefully I'll see you.